Welcome to Process Control lecture series. In my previous lecture, we discussed about the proportional control mode. That means in that lecture, we discussed continuous control mode and we discussed first one type of continuous control mode, that is proportional control mode. Now in this lecture, we discuss integral control mode. This is the second one type of continuous control mode. So now we start integral control mode. So what are the advantages of integral control mode? We discuss first here. So first one and most important advantage of integral control is eliminate the offset error problem by allowing the controller to adapt to change external condition by changing zero error output. That means we know in the proportional control mode, offset error is big threat. So here we use the integral action, so we can eliminate the action of the offset error. Now we start the working of integral control mode. So how it works? So the integral action is provided by summing the error over time, multiplying that sum by a gain and adding the result to the present controller output. So this is the simple working of integral control mode. If the error makes random excursion above or below 0, the net sum will be 0. So the integral action will not contribute. But if the error becomes positive or negative for an extended period of time, the integral action will begin to accumulate and make change to controller output. The analytical expression for the integral control mode is given by Pt is equals to Ki integral 0 to t ep dt plus P0. So here P0 indicates the controller output when the integral action starts, and Ki is indicate the integral gain. So this is the analytical equation for the integral mode. So here we can see the Pt is equals to Ki and integration 0 to 2 ep dt plus P0. Another way of expressing the integral action by taking derivative of equation 1. So we discussed what is equation 1 in my previous slide, which gives the relation for the rate of change of controller output with error. So here this is the derivation of equation 1. So we get dp by dt is equals to Ki into Ep. The equation 2 show that when an error occurs, the controller begins to increase or decrease its output at a rate that depends upon the size of error and the gain. So this is the equation number 2 indicate. That means what? If some error occurs, that means error is positive or negative. We discussed already what is positive error, what is negative error. Its output at a rate that depends upon the size of error and the gain. If the error is 0, controller output is not changed. If there is a positive error, the controller output being to ramp up at a rate determined by the equation number 2. Now we understand integral control action by help of this figure. So figure show two different value of gain. That means here you can see in the figure A, the graph is indicate the two gain K1 and K2. It can be observed that the rate of change of controller output depends upon the value of error and the size of the gain. So here you can see this is the K1 and K2 indicate the two different levels of the gain. That means here K1 is less than K2. So for that different gain we can see the performance of the integral control mode. So the figure B shows how controller output will vary for a constant error and gain. It can be observed that the controller output begins to ramp up at a rate determined by the gain. In case gain K1 output finally saturates at 100% and no further action can occur. So this is the working of integral control mode. Now we summarize the operation of integral control mode. So if the error is 0, the output stays fixed at a value equal to what it was when the error went to 0. That means output is at P0. There is no changes of the controller output. If error is not 0, the output will begin to increase or decrease at a rate Ki percentage per second for every 1% of error. What is Ki? So here Ki indicates the gain of the integral controller. Now we understand one term, area accumulation. So what is area accumulation? From the calculus, we learned that an integral determines the area of function being integrated. Here this is our equation for the integral control mode. Pt is equals to Ki EP dt plus P0. So thus the equation 1 can be interpreted as providing a controller output equal to the net area under the error time curve multiplied by Ki. We often say that the integral term accumulates error as a function of time. Thus, every 1% of accumulated error time area, the output will be Ki percentage. Now we discuss one example of integral control mode. So here an integral controller is used for a speed control with a set point of 12 rpm within a range of 10 to 15 rpm. The controller output is 22% initially. The constant Ki is equals to 0.15%. So here the Ki is given, controller output per second per percentage error. If the speed jump to 13.5 rpm, calculate the controller output after 2 seconds for a constant. So here we have to calculate the controller output for when the speed jump at the 13.5 rpm. So minimum into 100. So here we have the value of R, B, B maximum and B minimum. So now we substitute this value in this equation, that means in EP equation. So we get EP is equals to 13%, that means minus 13%. The rate of controller output change is then given by equation Pt is equals to Ki 0 to T EP dt plus P0. So this is the equation for our integral control mode. So now here EP is constant. So we can write this equation as Pt is equal to Ki EP into T plus P0. So here we have the value of Ki, EP, T and P0. So T is equals to after 2 seconds. So we can find out the controller output by substituting the value of Ki, EP, T and P0. So we get the controller output is equals to 31%. So this is the output when the RPM jump, after 2 seconds. Now what are the applications of this integral control mode? So first one application is in the general integral control mode is not used alone. That means generally in the industry we not use the integral mode alone, but can be used for the steam with a small process leg and correspondingly small capacities. So in this lecture we discussed about the integral control mode. So in this lecture we discussed what is integral mode, the working of integral control mode, what are the advantages of integral control mode, and we discussed one example of integral control mode. Thank you.